So thanks very much to QEC for inviting me. This is actually the first QEC I've been to. I think that's probably because I never worked on quantum error correction before. So I'm very happy to be part of this community finally with this work. And although there's no quantum error correction in the title, hopefully I'll convince you by the end that there is some quantum error correction going on in the content. So here's a kind of outline of where I'm going. So, and there's still no quantum error correction. Those words still don't appear in the content, but just stay with me. I'm going to start, let's talk in two halves. I'm going to start by talking about Hamiltonian simulation, and I'll explain what that means. I probably won't go into all of this detail. And then in the second half of the talk, I'm going to talk about how we applied this kind of technology from really based in quantum complexity theory, Hamiltonian complexity theory, to this questions about holographic duality and ADS-CFT toy models. So let's start with Hamiltonian simulation. I'm in a computer science department these days, so I have to pretend to be a computer scientist. So one thing that we learned from computer science, and we learned back in the 1940s, is that, and perhaps it's one of the most important lessons, which seems trivial now, but it doesn't really matter where you store information, right? And it also doesn't really matter where you do your computation. What matters is kind of what the information is that you've stored and how you process it. And these days, we're very used to this. So these days you code something on an x86 CPU, but typically these days this machine that you're running your code on doesn't actually exist. It's actually being simulated. It's actually encoded inside some supercomputing cluster somewhere in the world. You're probably not too sure where that is. Maybe it's somewhere over here. Probably not. I think electricity is expensive in California. The data center is probably somewhere cheaper. But you don't really care. And this actually doesn't exist either. This is all being simulated on ET's smartphone. And the point of this is that you just don't care. As far as you're concerned, the code you're writing, this might as well exist. And it would not look any different from inside what you're doing. And this goes by the fancy name these days of virtualization or cloud computing. It's all the rage. Physicists have been virtualizing physics for much longer than the computer scientists. So I don't know if anyone recognizes this picture. Oh, wow, big audience. Usually someone does. Oh, there's a few hands. OK, I'm going to assume you know the answer. And would have told me that this is a picture of a model built by Antoni Gaudi as a model of the Sagrada Familia Cathedral in Barcelona. And this is, in fact, a model in string and sand that's modeling, using the physics of string in tension and under gravitational forces on sand, is modeling the physics of something completely different, which is stone in compression. And so Gaudi used this kind of model, this virtualization of the physics of this, in a completely different physical system to help construct this cathedral and make sure it stayed up. So physicists have been doing virtualization much longer than the computer scientists. And in quantum, we're also used to this kind of concept, not quite for 100 years, but for the last at least 2 decades, of doing this kind of simulation where we take something like an optical lattice or maybe an ion trap, and we use that to simulate the physics of something completely different, like a high-temperature superconductor, or at least that's the dream. And these kind of things this is not just theoretical. This kind of simulation, this kind of analog simulation or Hamiltonian simulation has been being done in the lab for over 10 years now, nearly 20. So this is what we call Hamiltonian simulation in quantum information theory, or what I'm going to call Hamiltonian simulation. There's another notion of Hamiltonian simulation. I just want to make sure you have the two distinct in your mind. One of these you can call physical simulation. We're building a system that kind of behaves in some sense in the same way as the one we want to study. The other is our wonderful Hamiltonian simulation algorithm, which is what we would do if we had a full-scale, scalable, fault-tolerant quantum computer. But unfortunately, we don't. But this is fundamentally different. Here you're building a physical system that behaves in a certain way that mimics something you're interested in. Here, you're simulating it on a computer. And these are kind of, a reasonable analogy is the difference between building a model of an aerofoil and putting it in a wind tunnel and doing a computational fluid dynamics simulation on a digital computer. So this is the type I'm talking about. OK, so here's our Hamiltonian simulation. Let me abstract that and try and answer this question of what exactly does Hamiltonian simulation mean. At the moment, we know it when we see it. People do it in the lab. But what actually is, really am a mathematician who works on physics in a computer science department. So I like to have definition that I understand, and that means math. So let me abstract this away. What are we doing when we're simulating one physical system with another? Well, somehow we're taking the Hamiltonian of this system, and we're mapping it in some way into the Hamiltonian of some different system in a way that somehow preserves the physics. Okay, and I'm just going to call this map E for encoding. Okay, so what I'd like to, despite Hamiltonian simulation being done very successfully, there wasn't any really careful theory about what Hamiltonian simulation meant. And so I would like to understand what maps E are allowed here that we could justifiably call a simulation. And to that we take another lesson from information theory and say, let's take an operational approach. Let's write down a list of everything we'd like to preserve under this map, and then see if that gives us an understanding of what this map has to look like. So here's one thing I'd like to preserve. I'd like to preserve all of the energy levels of the thing I'm simulating as something I could measure. So I'd like to be able to reproduce the spectrum, the energy levels of my original Hamiltonian. So I want the energy levels to be the same. I'd like all measurement outcomes on my simulator to be the same as the ones on the thing I'm simulating, so that I have a good simulation. I want the time evolution to mimic that of the original system. I'd like the partition function to be the same. Here's a slightly more subtle one, but if I'm simulating a many-body Hamiltonian, I don't want to have to solve the entire Hamiltonian in order to be able to construct my simulation. I want to be able to simulate each interaction separately and glue them together. Because if I have to solve the full Hamiltonian just to simulate it, there's no point simulating it. I already solved everything. So that's another property we want that local operators map, or that convex combinations or even linear combinations of interactions transform or mapped to linear combinations of their simulations. We might want to reproduce the effects of errors and noise on the original system. We might want to simulate that. And I could keep on listing more and more properties that we would like in our list of desiderata. There's one important one I've missed here, and that's that my simulation had better be a Hamiltonian. Otherwise, I can't build it at all. So I definitely need that my simulation, the output of this map, is Hermitian. Otherwise, it's not even a Hamiltonian. So I can take all of this list of requirements, and in fact, I'm going to rewrite this a bit. Let me write this more generally in terms of some A that's Hermitian rather than H, because we want this to hold for all measurements, right? So the Hamiltonian is one measurement, it's the energy observable, but there are lots of other observables, and I want to preserve those too. So in fact, what I just wrote down is equivalent to this. And it turns out that we have all of this list of requirements, and in fact, with that, we can actually characterize exactly what this map has to look like. And it has to look like this and nothing else. And in fact, this list of requirements is overkill. We actually already, just these top three that I've highlighted already imply this form. So if our transformation maps Hermitians to Hermitians, if it's spectrum preserving, and if it preserves linear combinations or even just convex combinations, then that's the only possible map of that form. And from that follows the fact that all of the physics then is replicated in A primed. The physics of A is replicated in A primed. Okay, so that's nice. We have a characterization of what these look like. The proof is extremely beautiful. It involves some very nice maths, which I'm not going to tell you about. But please go and read the paper. Let me just unpack what this equation means. This says that if this A primed is going to simulate the physics of A, then the only thing it can look like is up to a unitary. You put copies of H down the diagonal and copies of the complex conjugate of H down the diagonal. You have any number of copies of H and any number of copies of H conjugate. And then up to a global unitary, that is the only things that preserve all the physics. Okay, so let me remind you, we started off by saying that we wanted to preserve energy levels, partition functions, measurement outcomes, time evolution, et cetera, et cetera. But I require them all to be reproduced exactly. And that's, of course, very, very strong and too strong, because real Hamiltonian simulations are never perfect. I haven't talked at all about efficiency. I care about efficiency. If I'm simulating a Hamiltonian on n particles, I don't want my simulator to have 2 to the n particles in it. I care about locality. So if I simulate something with local interactions, I'd like my simulator to have local interactions. I want local observables on my system to map to local observables on my simulator. Maybe I only care about getting the simulation right within a subspace. For example, in an optical lattice, the simulation's very good in the low energy subspace, but if you crank up your lasers to extremely high power, your experiment explodes, and that's certainly not replicating the physics of the original system. Right? So we can capture this by saying that we might only care about the simulation being correct within a certain subspace. And if I put all that together, I'm not going to go through it, but you can go through the same kind of exercise and derive what the form of the most general form of approximate simulations are. And I'm not going to unpack these equations here, but just to say that you can characterize this, you can read the exact characterization in the paper. Okay, so this says that if we simulate something up to errors epsilon and eta, which are two error parameters that kind of measure the errors in the eigenvectors and in the eigenvalues, below some threshold energy, so in the low energy subspace where delta can be big, but for all energies below delta, then we know what form this map has to take. So what is this is a bit hard to unpack, but let me show you what it means in pictures. So this means that the spectrum of my simulator looks like the spectrum of my original Hamiltonian up to epsilons, and then there's a big delta, a big gap, and then there might be some junk at very high energies. I've also required locality to be preserved here. So local observables on the original system map to observables on some small subset of particles, some constant size set of particles on the simulator. And now what physics are we replicating with this definition of approximate simulation? Well, again, you can prove theorems that show that this replicates all of the physics up to epsilon delta, as long as you're with energies below, up epsilons and etas, as long as you're at energies below delta. And you can also prove interesting theorems about the fact that noise in the simulator actually replicates the effect of noise in the simulation. That's an extremely important theorem, and it's important that it goes in that direction for justifying analog quantum simulation, the fact that there's no error correction in those experiments. But that sort of hints at some connection with quantum error correction. And indeed, actually, everything I've talked about, I've talked in very physics terms, but actually this is very closely connected to quantum error correction. Remember what my formula for my equation for the most general form of perfect simulation looked like if I have no errors? Well, up to an encoding isometry that puts this into a low energy subspace, it has to look like copies of A and copies of A conjugate. There should be a conjugate here. What does a quantum error correcting code look like? Well, it maps operators under an isometry with one copy of A. So a quantum error correcting codes are special cases of perfect simulations. There's a special case where I have P equals 1 and Q equals 0. And my approximate simulations, if I take the definition of approximate simulation, this is for P equals 1 and Q equals 0, this gives me an approximate quantum error correcting code. So these simulations are generalizations, are a generalization, or one way of generalizing quantum error correcting codes to something slightly different. Good. Here's another lesson from computer science that you probably know. There exist computers that can simulate all other computers. So with this machine here, a Turing machine, someone actually built one, thing with ticker tape that moves it left and writes symbols on it and reads them. We can actually simulate a desktop computer and a supercomputing cluster and even ET's smartphone. Slowly, but nonetheless, everything you can possibly compute, you could simulate it on this very primitive device. So that kind of raises the question, there are universal classical computers, there are universal quantum computers too. Are there universal quantum Hamiltonians? And what do I mean by universal? I mean, are there classes of other Hamiltonians that are able to simulate all the physical properties of any other system to any accuracy we like? So this is an extremely strong requirement. I've captured what it means to simulate by saying it's got to preserve all of the physics, up to arbitrary small errors, and for any other system. And surprisingly, it turns out that these do exist. So we even have a complete classification, at least for 2-qubit Hamiltonians, for nearest neighbor, sorry, not nearest neighbor, for interactions between pairs of qubits. If your Hamiltonian is built out of 2-qubit interactions, we know exactly which ones are universal and which ones are not. I'm not going to talk in detail about the result, but I want to mention a little bit about how we prove this. And the key idea behind this proof is that of perturbation gadgets, which is an idea that comes from Hamiltonian complexity theory. So perturbation gadgets are just undergraduate perturbation theory in quantum mechanics, but done rigorously. So you have some Hamiltonian, which has some, typically in perturbation gadgets, you think about, have some Hamiltonian that's very, very strong and some other weak interactions in our Hamiltonian. And as you probably remember from undergrad, I can do a perturbation series expansion in terms of the weak Hamiltonian, and I get some approximation to the Hamiltonian in the low energy subspace. So perturbation gadgets are constructed using that idea, but you just bound the errors rigorously, rather than just truncating the perturbation series and hoping it's small. So how does this kind of idea work? Well, here's one gadget we used in this proof of this complete classification result. If you take this little gadget here, so each of these are qubits, and all the interactions between these are Heisenberg interactions, so xx plus yy plus zz. If you restrict to the low energy subspace, or the ground state subspace of this Hamiltonian, turns out that what you have is a two-dimensional degenerate ground state subspace, i.e. a qubit. Now if I take two of these little gadgets, and I make the interactions within this tetrahedron very strong, and then I connect it with another Heisenberg interaction that's order 1 instead of order delta in strength, and then I look at what does the Hamiltonian look like when I restrict to the subspace of states with energy below delta. Well, it turns out what you get is now we know we're going to get the Hilbert space is going to look like two qubits, but the interaction between them, the effective interaction you generate, up to 1 over polynomial and delta errors, looks nothing like the Heisenberg interaction. So the Heisenberg interaction has full SU2 symmetry, and this has broken the SU2 symmetry. So this is a gadget that lets us escape from the symmetry constraints in our Hamiltonian. So that's an example, and there are many examples in the Hamiltonian complexity literature of gadgets that do various different things and let you glue together Hamiltonians in a way that generates new Hamiltonians. Again, this is something that's familiar in physics. This is very similar to what's going on in where you derive a low energy effective theory in condensed matter or in high energy physics. Okay, here's the actual full proof. Involves chaining together a huge number of gadgets. It's a bit long, but at the end of the day, we understand that not only can we construct these universal Hamiltonians, we also can characterize them, at least for when we have two qubit interactions. And the nice thing about this theorem is now half of Hamiltonian complexity theory just follows from this classification theorem now, plus a whole bunch of new results. And what I want to talk about in the rest of this talk is one of these new things that comes out of this work. Okay, so now you know what Hamiltonian simulation is, and you know that there exist universal Hamiltonians. Let me switch gear and talk about holographic duality. And luckily, Sephir has done a great job of giving you an introduction to this, so I'm going to go somewhat quickly. But in case it's not familiar, let's refresh your memories of what Sephir told you this morning. So the idea of ADS-CFT, of this holographic duality and quantum gravity, is that somehow quantum gravity in some bulk theory somehow is the same as, or maps to, some conformal field theory on the boundary of this bulk. Okay, so people always draw this soup can model. This is kind of a toy picture of cartoon of ADS-CFT where you have a two-dimensional bulk and a one-dimensional boundary. Typically in quantum gravity, these dualities occur in much higher dimensions. Good, but this should sound kind of familiar given what I said in the first half of the talk. If we're going to simulate, if the physics on the boundary is going to be somehow the same physics as the physics in the bulk, well, we now have a mathematical understanding of what that has to mean. It must mean that the boundary Hamiltonian should be related to the bulk Hamiltonian by one of these simulation maps. But this bulk boundary duality has some rather interesting geometric properties. So for example, if we take an observable somewhere in the bulk and we construct a geodesic in the bulk to the boundary, then it's a property of ADS-CFT that if I want to recover the expectation value of the observable here, on the boundary, I need to measure an expectation value of an observable that acts only in this region here. And as Sephir told you, this implies that this means that if I trace out the rest of the boundary here, I must still be able to recover the expectation value of this observable, even if I've lost the rest of the boundary. But this boundary that I can recover from is not unique. If I drop a geodesic in a slightly different direction, I get a different region of the boundary that I can recover from. So we have the fact that not only is the information encoded in a way that protects it against erasure errors, it's also redundantly encoded in that I can erase different bits of the boundary and still recover the same information. And this holds for all observables. So it holds for all the observables. This means we can reconstruct the qubit that was encoded that's here in the bulk. So this implies that we have a quantum erasure code that protects against erasure errors on certain regions of the boundary. What's more, this holds no matter all of the points in the bulk. So it doesn't matter where I put this observable or where I put this qubit. the same thing applies. So a qubit over here, I can recover from these regions. A qubit much closer to the boundary can only be recovered from smaller regions. Deeper in the bulk, it can be recovered from larger regions, and it's more redundantly encoded. So these are quantum error correcting codes, but with a very unusual geometric structure. And these have become known as holographic codes. So it's not a formal definition, but a holographic code is a quantum erasure code with some weird locality structure. There's my non-precise definition of it. So this kind of structure was understood first that this is a consequence of what's believed to happen in ADS-CFT. So then the question is, well, can one actually construct such error-correcting codes? And the answer is yes. And the first example, as far as I'm aware, was something called the now, it always gets called the happy code. Unfortunately, in the paper, they put the author names in the wrong order. But yeah, too late to go back and correct that, I guess. Everyone calls it the happy code for Harlow, Preskill, Postavsky, Yoshida, permuted. And they constructed an explicit example of such a holographic code using tensor network constructions. So this gives so what's the idea behind this construction? You have they put a tensor at each site in the bulk, and they join them up. And so this tensor is actually the encoding isometry of an error correcting code, and then think of it as a very highly concatenated code. So then this is the logical qubit, outcome 5 physical qubits. This is a 513 code, and then encode each of those physical qubits in another layer of encoding, but you also bring in a new logical qubit at the same time and keep on pushing this out. And you get this, the structure of the tensor network is what gives you the geometric properties of the code. And this was a really nice result. It gives a toy model exhibiting a concrete toy model that you can play with and reason about and prove things about that exhibits a lot of the qualitative features of the ADS-CFT duality. It's not a model of quantum gravity. There's no gravity here. But it has a lot of some of the qualitative phenomenology of it. So this gives a duality between bulk and boundary, states and observables. But ADS-CFT is not just a duality about observables and states. It's also supposed to be a duality about models. So including the time dynamics, the energies, the whole physics, not just static things. And in these toy models, this means that ADS-CFT, a toy model, ought to also encompass a duality between bulk Hamiltonians, local Hamiltonians in the bulk, and local Hamiltonians in the boundary. So let's see what happens when we use the happy code to do such a duality, to see what Hamiltonians in the bulk map to on the boundary. So let's imagine I have a local Hamiltonian in the bulk. So let me just take one of its interactions and let's map it to the boundary. And I get some interaction on the boundary, and because this is a perfect error correcting code or a perfect simulation, I know that that Hamiltonian is reproducing the same physics of this interaction. But now what happens if I take an interaction that's deeper in the bulk? Well, I drop geodesics down to the boundary, but this gives me a very, very large region of the boundary that this maps to. So this local interaction here between nearest neighbors becomes a very non-local interaction on the boundary. So you can do this duality. You get a perfect simulation in my terminology, or in the Hamiltonian simulation theory terminology, but it's between local Hamiltonians in the bulk, but it maps them to global Hamiltonians on the boundary. And once you've got a global Hamiltonian, you don't have any relevant geometric structure anymore. So this isn't yet, and this is why in the happy paper they didn't talk about dualities on Hamiltonians or dynamics, because they were well aware of the fact that whilst you can construct this, it's not that interesting on the level of Hamiltonians. So these holographic codes, or these tensor network models of holographic codes, give very good toy models for states and observables, but they don't work as toy models of dualities between Hamiltonians or between models. And that means we can't ask in these toy models, in these holographic code toy models, questions about energy scales or dynamics. But remember the first half of the talk, I said that there are universal Hamiltonians that can simulate any other Hamiltonian. And indeed, in this classification result, one Hamiltonian class of Hamiltonians that we showed was universal is the 2D Heisenberg model. So the model on a 2D square lattice, just with nearest neighbor Heisenberg interactions. Even that is completely universal if I'm allowed to tune the coupling strengths. So that kind of raises the intriguing possibility. What if we take these holographic quantum error correcting code constructions, which we know are special cases of simulations, we put it together with all of this machinery we developed for Hamiltonian simulation and proving the existence of universal Hamiltonians and constructing them. Can we improve these toy models of ADS-CFT duality to extend them to dualities on local Hamiltonians, and then start asking about dynamics and energies. Here's the problem, or one problem. The happy code and most of the other tensor network constructions take a 2D bulk and a 1D boundary, and our perturbation gadget techniques only work in 2D, so we need a 2D boundary, and we only have a 1D boundary, so they don't work for this setting. So first thing we have to do is to generalize these holographic code constructions. We need a 3D, at least a code that goes from 3D to 2D. So okay, we had to do that first. To do that, it's a little bit more difficult, largely because you can't draw pictures like this and think about it. It's very hard to think about tensor networks embedded in 3D hyperbolic space, or it's hard for me, maybe you can do it. So to do this, we have to exploit more of the mathematical structure of these codes in order to give us a mathematical handle on being able to prove the properties we need. To do this, I'm not going to go through definition, but what we used is is the theory of hyperbolic Coxeter groups, which gives us, not groups, hyperbolic Coxeter groups. And this gives us this just gives us a machinery to generalize this kind of construction to higher dimensions. So you can think of the happy code as being a tessellation of 2D hyperbolic space by right-angled pentagons. And what we did is to generalize this kind of idea, but now to tessellations of 3D hyperbolic space by right-angled dodecahedra. And here's a picture of it. I don't know about you, I find it very hard to just look at this and derive theorems. So we need to go to this mathematical structure of the groups that are behind, the symmetry groups behind this. Okay, the Coxeter group structure, I'm not going to tell, it's really beautiful stuff, but I don't have any time to tell you in detail about it, but it lets us prove things about the geometry using algebra. So for example, we use this to prove that the bounding surface of a finite portion of this tessellation is homeomorphic to a two-sphere. And it lets us, now what we do to construct our holographic code is we put a tensor at the center of each of these dodecahedra, connect it by legs to all of the neighboring 12 dodecahedra, plus a 13th leg that's coming out, that's our bulk qubit, and then we connect them all together in a network, and we get something that's the analog of the happy code in higher dimensions. And of course, it's unfortunately not quite that simple. So we need to match up the rank of the tensors to the classification of 3D hyperbolic groups. They don't exist in all possible, there's a classification, at least in 3D, of most of these. We need to match up the tensors we construct. The qubit ones just don't exist, so we have to go to qdits. Most of the machinery hasn't been done, the mathematics hadn't been done in other papers for qdits, so we had to prove those things first. So we have to generalize MDS codes to qdits, and this is how you construct the perfect tensors. We have to look at the scaling of stabilizer weights and support when pushed through the tensor network, but these are now qdit stabilizers. We have to construct new perturbation gadgets because people had almost exclusively done them for qubits. But okay, this is all very nice, and I suspect some of these theorems or lemmas have uses, other applications in quantum error correction and in other areas of quantum information. So if you want to hear about that, either go to the paper or talk to Tamara Kohler, who's in the audience, who's my co-author on this paper. But having done all that, what do we get after all this work? So we now have an encoding isometry for a holographic quantum error correcting code defined by this tensor network in 3D hyperbolic space. So now let's take any local Hamiltonian in the bulk, and let's push it through this tensor network to the boundary. And we get some boundary Hamiltonian that's a perfect simulation of this. So it reproduces all the same physics, but as before, it's totally non-local. Great. Now what we do is we construct an approximate simulation of this boundary Hamiltonian on a surface that's just very slightly further out from the surface of this section of this hyperbolic honeycombing. So we take a surface here, and now we use our universal Hamiltonian machinery. Unfortunately, we can't just use the theorem. We have to redo the proofs in this context and work things out in detail. But we can use that machinery to construct an approximate simulation on this surface of this Hamiltonian. But now this approximate, because of the magic of this Hamiltonian simulation and perturbation gadgets, now this Hamiltonian we can make it local. But it's also an approximate simulation of this Hamiltonian, which is a perfect simulation of this Hamiltonian. So we know, because we proved it in the sort of mathematical theory of Hamiltonian simulations, that as long as we've got simulations, all of the physics of this is replicated here, up to epsilon, errors epsilon and eta, and as long as you're below some high energy cutoff delta. And so now we have this, and simulations compose, so this simulates this, which implies that this is an approximate simulation of this guy. So we have what we want, but now we have a local Hamiltonian on the boundary rather than a global one. Okay, so now what about the scaling? If I have an n-qubit Hamiltonian in the bulk, then I only pay a logarithmic overhead. It's the same, up to log factors, it's just linear. It just scales linearly up to log factors in terms of how many qubits I have on in my boundary Hamiltonian. This surface is very, very close to the surface of the bulk that I'm dual to. It's only a distance log n away from the n edge of this finite piece of bulk Hamiltonian. So the scaling actually works out very nicely. And what about the errors? Well, you can make the errors in our simulation arbitrarily small if you crank up this energy scale delta arbitrarily large. So this means that this delta appears in the Hamiltonian, so this means I'm making some of the interactions in my Hamiltonian extremely strong. And if I want the errors to go to 0, I have to make this Hamiltonian unbounded. And in Hamiltonian complexity theory, this is something people are not always very happy with. Things usually scale polynomially, but still you'd like something where you don't have very large energies in your Hamiltonian. But this is high energy physics, so I really don't care. I'm very happy to have Hamiltonians with really high energy scales. If I think about a field theory, the operators in my field theory are unbounded. So actually, just in this context of ADS-CFT, I really don't care about the fact that to get good simulations, I have to have large energy scales on my Hamiltonian, because that's kind of what I expect in high energy physics. Good. So we heard in the last talk about Easton-Knill theorem, and I mean, luckily these no-go results came out after our paper. Otherwise, I'm not sure if I would have had the confidence to work on this. So the order is sometimes it's good not to know things, but the Easton-Knill theorem was out before our paper, and it says you cannot have a continuous family of transversal gates in the quantum error correcting code. Sefer has told you about this much better than I'm going to. But now let's think about what this means for this bulk boundary duality we've constructed. If I take a bulk Hamiltonian, let's take a very simple bulk Hamiltonian. Let's take a non-interacting Hamiltonian. So each Hamiltonian term just acts on one particle, and there are no interactions at all. If I take the time evolution operator corresponding to that, well, then I get a tensor product of unitaries, acting one on each side on the boundary. Apply our construction, well, you now get a quantum error correcting code that maps the time dynamics of this, which is just a tensor product of unitaries, to the time dynamics on the boundary, which is a tensor product of unitaries. And this looks pretty transversal to me. So why do we not have a contradiction with Easton-Knill? Well, the reason is that Easton-Knill only applies to perfect quantum error correcting codes, and our error correcting code is an approximate error correcting code that you can make arbitrarily precise but not perfect. So this is why this doesn't contradict, our construction doesn't contradict Easton-Knill. But now there are these generalizations of Easton-Knill by Sefer and co-authors, and also there's nice work by Misha Woods and Alvaro Alhambra as well, where they looked at generalizing Easton-Knill to approximate quantum error correcting codes and to interacting Hamiltonians. And here's the bound from Sefer's talk written in my notation. It says that the errors have to be at least as big as the order of the norm of my Hamiltonian divided by n times delta. And in our code, for any number of bulk qubits, we can make the errors arbitrarily small. But as I said in a few slides back, to do this, we have to take delta arbitrarily large, delta large. So this actually doesn't, our construction escapes this no-go theorem as well by the fact that it's completely consistent with it, which is good, because otherwise one of the two papers would be wrong. So it just squeezes into the freedom allowed in these stronger generalizations of Easton-Knill. But it gives a non-trivial example that's now where you are mapping a unitary dynamics generated by overlapping generators. So a local, because our construction doesn't just work for non-interacting Hamiltonians, it works for any Hamiltonian, to something on the boundary that has the same symmetry, as well as many other, same time dynamics. I should mention there are also lots of other constructions in the literature of trying to get time dynamics into ADS-CFT. So you heard about Cephir's in the previous talk, which is not exclusively about that, but it also applies to the time dynamics, which you can think of as time translation symmetry. The paper by Woods and Alhambra also have a nice construction that takes any quantum error correcting code and turns it into an SU1 invariant quantum error correcting code. So you can think about this as it gives you the time dynamics on the boundary. But unfortunately, that only gives product representations on the boundary. So that only works for non-interacting Hamiltonians in my language. Steigman and Osborne have a really nice construction where they can construct holographic quantum error correcting or quantum states, tensor networks which approximate stronger symmetries like conformal symmetry. But unfortunately in their construction there aren't really any Hamiltonians at all. So at the moment our perturbation gadget construction is the only construction that works to map interacting Hamiltonians, local Hamiltonians in the bulk to interacting local Hamiltonians on the boundary. And the nice thing now we have that is we can now start to ask fun questions about what happens in ADS-CFT, but now we can ask questions about dynamics and energies, which you couldn't ask before in these toy models in a meaningful way. So in the last 5 minutes, let me tell you about some piece of this. I'm not going to have time to talk about boundary to bulk mappings. This is something that ADS-CFT people care a lot about, but I'm going to instead talk about something even cooler than that. I got to talk about black holes, right? So back in the Happy paper, they proposed what a black hole might be in these toy models. So this is a toy model of a black hole. It's just something that replicates some of the qualitative features of black holes in this toy model, remember. This is not a full-fledged theory of quantum gravity. But their proposal was simply that a black hole corresponds to deleting a tensor in this network. And this looks very trivial, but it's actually kind of nice because when I delete a tensor here, I now have extra free legs. In quantum error correcting code language, I've just now changed to a code with extra logical qubits. And they propose that these extra qubits, bulk qubits, correspond to the degrees of freedom of a black hole that's sitting here. And because of the structure of the tensor network, the number of degrees of freedom that you introduce, the extra number of qubits you introduce, scales with the boundary of this black hole, which matches up with what you would expect from the Bekenstein-Hawking bound. As I make this black hole bigger, the entropy or the number of degrees of freedom or the information stored there that can be stored there scales with the boundary, not with the volume. So okay, it's a simple observation, but it's a kind of nice toy model that you can think about. Does this kind of make sense? One thing you would like is to know that black holes are high energy states in the real world. So in the Happy code itself, you couldn't really ask about what's the energy of this black hole you've placed there. But with our Hamiltonian duality, now we can ask what's the energy when we take one of these black hole states with respect to our boundary Hamiltonian that simulates all of the bulk physics. And it's exactly what you would hope. The black hole states have energy that's much, much higher than things with no black holes. So let me tell you a little bit about how that works. I'm going to draw the pictures in 2D because it's easier. In reality, everything I'm saying only works. We only know how to make it work in 3D or higher, but I'm going to draw 2D pictures. So my boundary Hamiltonian, this is the physical space of a quantum error correcting code. So this has the code subspace, which is with respect to our Hamiltonian, is the ground state subspace of this Hamiltonian. But there's also a whole load of the other Hilbert space, which is outside of the code subspace. And in fact, if we construct the Hamiltonian for our code in the right way, we have that we can break up the boundary Hilbert space, so the physical Hilbert space, into a direct sum of pieces. One of the lowest energy piece is has energy 0. The next piece has low energy at least. The next piece has energy, and then another piece that corresponds to something with one black hole, which has energy delta. And then if we have 2 black holes, that lives in a different part of this direct sum with energy 2 delta, and so on and so forth. So our Hilbert space on the boundary breaks up into a direct sum over subspaces that the lowest energy one corresponds to the complete tensor network, the next highest one corresponds to a tensor network with 1 hole, the next highest one in energy corresponds to a tensor network with 2 holes, etc. All of these geometric structures are there in the boundary in a direct sum. So on the boundary we can talk about superpositions of these bulk geometries. And this is the way you should think about ADS-CFT. You should think about it as thinking about what the geometry of the bulk emerging from the states on the boundary, rather than the other way around. Okay, and now we can ask, so now we have a nice thing that the more black holes you put in, the more energy it has with respect to a Hamiltonian. And now we can also talk, we have a Hamiltonian, so we also know how bulk dynamics maps to boundary dynamics. So let's take some cool dynamics in the bulk. Let's assume the bulk dynamics is that of gravity, and let's start with a shell of matter somewhere out near the edge that's got very low energy density. And now let's start it in this state, and now let's let this evolve under gravity. What does it do? Well, it collapses down to the middle, and if there's enough mass there, it collapses. Let's just say it's a shell of matter, and it collapses inwards to the middle. And let's now ask, what does this dynamics in the bulk look like on the boundary? What does it have to look like on the boundary in our construction? So let's take the boundary. I start off with excitations on the vacuum that live near the boundary, so I know how to map them to the boundary, sorry, that live near the boundary, so I know how to map them to the boundary. They become a whole set of small local operators applying excitations to the ground state of my Hamiltonian on the boundary, but all of these are local on the boundary. Now I evolve things in towards the middle. Well, now we know that when we drop geodesics from something in the middle, this spreads into something that covers a very large region of the boundary. So now what's happened? Our state on the boundary has started off in a product state, something that's very has very little entanglement, and it's evolved into something that has very high entanglement on the boundary. And this is exactly what people expect in ADS-CFT, that states, if this is like got enough energy to collapse to a black hole, we expect high energy states and black hole states to correspond to highly entangled states in the CFT. So finally, let's look at what's going on in a bit more detail. So now, I start with it, let's look at the energy scales in this. I start with this thing, this state on the cannot violate very many stabilizers, violate any stabilizers, because I'm going to assume this is just a state that is low energy, there are no black holes. So this means it lives in the code subspace. That means it doesn't violate any stabilizers in my code. But let's imagine this state has enough energy to form a black hole, but it's not high enough energy density. Then that must mean that the energy of this state is bigger than my black hole energy scale in my Hamiltonian, but the energy density is too low to form a black hole. Okay, so that's what the boundary, this initial state has to look like. Now when I evolve it to the final state, this dynamics is unitary, so energy is preserved. So I know that the final state also has energy bigger than my black hole energy scale. But now all of this state looks in the bulk like something where I just apply an operator an excitation at the center. That can only violate, in my error correcting code, stabilizers that come from just a few stabilizers near the center. But these don't have, these stabilizers don't have, you can't pick up enough energy from you can't pick up enough energy from this Hamiltonian unless you actually violate one of the stabilizers and pick up energy bigger than delta S by breaking a stabilizer term. And we know what breaking a stabilizer looks like. It means we don't have that tensor anymore in our tensor network, and we've created a black hole state. So with this Hamiltonian simulation, Hamiltonian complexity construction of this duality, we now can see in these toy models how black holes actually have to dynamically emerge from this, along with all of the other static features of the ADS-CFT duality and interesting error correcting code features. It also naturally falls out that the kind of dynamics and energy scales that you expect from ADS-CFT, we're kind of forced to have them there in these, when we extend these dualities to Hamiltonians. Okay, so with that, I'm going to finish. I'm just going to put up the references. So the paper on Hamiltonian simulation was with Ashley Montanaro and Stephen Piddock. And as usual, the students on these papers did almost all the work. So Stephen who was then a PhD student, did a lot of the work on this paper. And on the holographic duality, Tamara Kohler is in the audience. The paper is in this archive reference and will be here in JHEP soon. And again, Tamara did 99% of the work on this paper. So if you want to know about details, she's in the audience, and go talk to her in one of the breaks. So thanks a lot for listening.
Great. We have time for a few questions.
When you constructed your three-dimensional mapping between the bulk Hamiltonian and the boundary Hamiltonian, you used perfect tensors?
Yeah.
Is there any reason that you have to use perfect tensors?
No. It's just convenient. You could, like some of the other constructions in the literature that use random tensors, they almost certainly work. You have to do all of the work to prove it. But yeah, there's no particular reason except convenience. Yeah.
What particular kinds of convenience?
So one thing you want to prove is that you have an isometry from bulk to boundary, ideally. That's, of course, by construction if you use perfect tensors. If you use something else, you might have an approximate isometry. That will be fine, but you have to prove it, and you also have to ask about what's the scaling of, as you push things through this, how do the errors scale, and how does the weight of the stabilizers, if it's still a stabilizer Hamiltonian or stabilizer error correcting code, or the weight of the Hamiltonian terms if it's more general. So all of these things get just harder to prove, and it's kind of hard enough. But yes, I think you can generalize this. It would be very interesting to do. Someone should do it.
Okay, thanks.
Another question? Yes.
Thank you for a very good talk. I have a question regarding your universal Hamiltonian
Sure.
result. So you said that there is a universal Hamiltonian that can simulate any other
That's right.
Hamiltonian. And my question is related whether you have some similar results for local Hamiltonians, for example, in d dimensions. For cellular, this result reminds me some similar result from cellular automata when, for example, in 2 dimensions you have a game of life that can simulate any other cellular automata. Is there something similar here?
So I didn't have time to talk about this result in detail because I wanted to get on to talking about the holographic quantum error correcting codes. But indeed, the result we proved shows that, for example, the 2D Heisenberg model on a 2D square lattice can simulate any Hamiltonian in any other dimension. So you can simulate something in 5 dimensions in 2. You pay a small price, and it's a local simulation in the sense that a one-body operator in the 5-dimensional space maps to a one-body operator in the simulation. A 2-body operator also maps, but if your 2-body operator in 5 dimensions is nearby, there's no continuous embedding of 5-dimensional space into 2, so it's still a 2-body operator in the simulation, but now it's not necessarily geometrically local anymore. You lose something by embedding higher dimensions into smaller, but it's still a local in the sense of if it starts off as 2-body, it's still constant times 2-body in the simulation. So we already have a result somewhat like that. It would be very cool to think about applying this kind of stuff not just to ADS-CFT duality, but to other dualities. I think that's a nice question.
I also have a question, what about 1 dimension? You have a negative result.
I think we might be able to construct universal Hamiltonians in 1D, but it's still work in progress.
Thank you.
Great. Let's thank Toby again.